Hello everyone, welcome back to my channel. Today we're going to go over this problem. Let's first read the problem. Streams of water from two tanks impinge upon each other as shown in the figure. If viscous effects are negligible and point A is a stagnation point, determine the height h2. So to use Bernoulli's principle or equation, which is really another way of writing conservation of energy, we have to know the underlying assumptions because it is one of the most misused equations in fluid mechanics. Assumptions are that the fluid is at steady flow, there is no friction, that is, that the viscous effects are negligible, and that the fluid flows along a streamline, and that it is incompressible flow. So, this is a Bernoulli principle problem. And basically, are all of these met? Yes, it is steady flow. Um, there is no friction because viscous effects are negligible and it flows along a streamline, aka streams, and it is incompressible flow because it's water. So Bernoulli's principle is a fundamental concept in fluid dynamics that describes the behavior of a moving fluid, either liquid or gas. And Bernoulli's principle states that in a streamline flow, the sum of pressure energy, kinetic energy, and potential energy per unit volume of a fluid is constant. In simple terms, when the speed of a fluid increases, its pressure decreases, and vice versa. This is the reason why airplanes fly, because the speed of the fluid moving moving on top of the wing is faster than the speed of the fluid moving below the wing, and thus there's a net pressure upwards, and thus it creates a lift, and that's why the airplane flies. In mathematical form, this is as such, where P is the pressure of the fluid, rho is the density of the fluid, v is the speed or velocity of the fluid, g is the acceleration due to gravity, h is the height above a reference point, and each term represents P, represents pressure energy. 1/2 rho v squared represents kinetic energy per unit volume. Rho gh represents potential energy per unit volume. The key implication is that a faster fluid creates a lower pressure and slower fluid is higher pressure. Examples in real life is airplane wings, Venturi effect, and slower shower curtain effect. When you shower, faster moving air pulls the curtain inward due to a pressure drop. So as you see over here, the Bernoulli equation is a fundamental principle of fluid dynamics and states that the sum of static pressure, dynamic pressure, related to velocity, and hydrostatic pressure related to height remains constant along a streamline in an ideal fluid. In essence, the equation represents the conservation of energy for a moving fluid, where increases in velocity are compensated by decreases in pressure and vice versa. The most common form of the Bernoulli equation is as such, where P is static pressure, V is fluid velocity, rho is density of the fluid, G is acceleration due to gravity, and Y is the height or elevation. Assumptions for applicability. It must be steady flow because fluid properties like velocity, pressure, and density do not change at any given point over time. The fluid must be incompressible. That is that the fluid's density remains constant even with varying pressure. It's an inviscid flow, which means that the effects of viscous friction are negligible and no heat addition. That means there's no significant amount of heat added to or moved from the fluid. What the equation means. The Bernoulli equation is a statement of conservation of energy showing how different forms of energy are interconverted in a fluid. Static pressure P is the energy associated with the fluid's internal pressure. Dynamic pressure is 1/2 rho v squared, which is the kinetic energy per unit volume of the moving fluid. Hydrostatic pressure is rho gy, which is the potential energy per unit volume due to the fluid's height. In simple terms, as the speed of the fluid increases or dynamic pressure increases, its static pressure decreases and vice versa, maintaining a constant total energy along the flow path. Let's say let's see what if it's in our equation sheet. And sure enough, it is in our equation sheet as this rho over P pressure over rho G plus V squared over 2G plus Z is equal a constant for inviscid flow. Over here, they simply divided by G instead of multiplying by G. But in our other form of Bernoulli equation, it looks slightly different, but it is saying the same thing. And also in our equation over here, the equation is a little different, but it is saying the same thing. They just divided it by G and by rho, I believe. Yes, so as you can see, they just divided by rho and by G. I'm not sure why actually, but it's okay. So the Bernoulli equation relates fluid pressure, velocity, and height, while a stagnation point is a location where fluid velocity is zero. So applying the Bernoulli equation to a stagnation point shows that the static pressure is maximum there, as all the fluid's kinetic energy or dynamic pressure has been converted into pressure energy, resulting in a stagnation pressure. So, yes. So first we're going to apply Bernoulli's equation from point 1 to point A to solve for PA, the pressure at A. And then we're going to apply Bernoulli's equation from point 2 to point A to solve for H2. So first, applying Bernoulli's equation from point 1 to point A, we have that the pressure over rho G plus V squared over 2G plus Z, which is the height at A, is equal to pressure over rho G plus V squared over 2G plus Z 1 prime. So P1 is given as 25 psi G, and we want to find PA. V1 is about 0. So V1 is the velocity at the air water interface, and basically the velocity there is around 0. And VA, the velocity at A, is also 0 because it's a stagnation point. And Z1 is going to be equal to H1, and ZA is going to be equal to H3. So ZA is going to be this height over here, which is H3. Sorry, and then Z1 is going to be H1. So from the first velocity equals 0 to the bottom. So basically, PA yes. So we have to apply Bernoulli's equation now to solve for PA. So P1 is going to be over here. So let me see, PA over rho G plus VA squared over 2G plus ZA, which is H3, is equal to P1 over rho g plus V1 squared over 2g plus H1. So certain things cancel out. So as we said, both VA and V1 are both 0, so these two go to 0. And we are left with PA over rho G plus H3 is equal to P1 over rho G plus V1 squared over 2G, wait, which is 0 actually, plus H1. Multiplying both sides by rho G, we have PA is equal to P1 plus rho G H1 minus H3. Okay, so over here we have energy per unit volume before and energy per unit volume after. So basically, this is an example of how to apply Bernoulli's principle and what we set equal to each other. So over here, we have flow velocity of 1 and flow velocity of 2. Basically, because of the constriction, the pressure energy changes, the pressure energy changes, which causes the flow velocity to increase. So at this point, there's an associated pressure energy, an associated kinetic energy, and an associated potential energy. Whereas as over here at this point, there's also an associated pressure energy, kinetic energy, and potential energy. So back to our problem. Basically, at point 1, there's an associated potential energy, pressure energy, and kinetic energy. And also over here at point A, there's an associated pressure energy, kinetic energy, and potential energy. And because it's flowing in a stream, these have to be equal to each other, the sum of these energies, because of conservation of energy. So now that we have PA at the stagnation point, we can go from point A to finally, let's call this P2. So what we can do here is, yes, or we can, yes, we can either apply it from point 2 to point A or point A to point 2, I believe. However, I believe that it is more usual to start from point 2 since that is an air-water interface rather than point A, which is just a stagnation point. So that's what I'm going to do. So Bernoulli equation 2 will be from point 2 to point A. So let's write the general governing equations. We have P over rho G plus, plus V squared over 2G plus Z times 2 or at 2 prime is equal to P over rho G plus V squared over 2G plus Z at point A. So basically, we have P2 for the pressure at 2, which is which is actually 0 gauge. Yes, so yeah, they give us P1, which is actually not zero gauge. And what this, oops, sorry. And what this G means is actually it's 25 pounds per square inch gauge, which means that it's relative to atmospheric pressure. It's already gauge. So that's why we'll use gauge pressure on the other side. So we have P2 over rho G, rho is the density of water, plus V1 squared over 2G. Wait, sorry, V2 squared. 2 squared over 2G. Plus Z2, which is the distance from point 2 to point A, which is H2. And we set this equal to PA again over rho G plus VA squared over 2G plus mm, wait, sorry. Actually, Z2 is actually equal to H3 plus H2, and ZA is going to be equal to H3. Yeah. So yeah, so the pressure at 2 is going to be zero gauge. So let's just write zero gauge. The velocity at 2, um, there's going to be no velocity there as well because it's a water-air interface. So V2 is about 0. Yeah, so this whole term goes to 0. And Z2 is equal to H2 plus H3. And it's basically the potential energy at that point. And the potential energy is directly related to the height above the ground. So PA is going to be what we found earlier. VA squared over 2G again is 0. And ZA is H3, the distance from point A to the ground. So we have that H2 plus H3 is equal to H3 plus P1 plus rho G H1 minus H3 over rho G. And we have to solve for H2 right now. So H2, solving for H2, we have P1 over rho G plus H1 minus H3. We have this general expression. So H2 is equal to P1 over rho G plus H1 minus H3. And we can now plug in known values. We know that P1 is, for instance, 25 pounds per square inch gauge. So it's equal to 25 pounds per squared gauge over the density of water or the specific weight. The specific weight, I believe, wait, is it called specific weight? Rho G. Yes, the specific weight is gamma equals rho G. Um, yes, so rho G, and rho G is the specific weight for water, and that value is actually 62.4 pound. Wait, okay. Don't know what's going on. Okay. Yes, so 62.4 pound force per feet cubed, and then uh plus h1 minus h3. So it's 8 minus 20 feet. Turning, and this one is going to actually be 12 squared inches squared over feet squared. So let's compute that out. And h2 will be equal to, so it's equal to 45 .7 feet. Thank you for watching this video, and I hope this video was helpful for you guys in knowing how to apply Bernoulli's equation. And I'm gonna post these slides afterwards, and thank you guys again so much for watching. Bye.